You have fallen into Event Horizon with John Michael Godier. Joining John today is Amir Siraj. Amir Siraj is a theoretical astrophysicist and concert pianist. He is currently pursuing his PhD at Princeton University's Department of Astrophysical Sciences. CNN called his work one of 10 extraordinary cosmic revelations in 2022, and he was the youngest scientist named to the Forbes 30 Under 30 list in 2021. Recently named one of Astronomy magazine's 25 rising stars, Siraj seeks to understand the solar system in the context of its cosmic environment through research topics including interstellar objects, asteroids and comets, planetary system formation and evolution, supernovae, black holes, dark matter, and the search for life in the universe.
Amir Siraj, welcome back to the program.
Thanks for having me back, John.
Amir, you have a new paper out, and it's absolutely fascinating because it seems to me to lend an interesting line of credence, perhaps even a separate line of credence, towards the idea of there being one or more additional planets, potentially large, in the outer solar system. The so-called Planet 9 or Planet X, if you prefer, or even Planet 10, Planet 11. We don't know what's out there. Now, give us an overview of the new modeling you did with this new paper and how it relates somewhat independently to what we know about the weirdness of movement in the outer solar system that's pointing towards the existence of such planets.
Yeah, absolutely. So, there has been basically 176 years of both searching for a giant planet beyond Neptune and hypothesizing about possible giant planets beyond Neptune, or let's just say massive planets broadly, that they don't even have to be giant. And it's spanned a large range. It spanned a large range of different approaches. One of them was in the early 1900s, and it was sponsored by Percival Lowell, who founded who founded the Lowell Observatory in Flagstaff, Arizona, which actually ended up finding Pluto. But notably, in the past, let's say, decade or so, there have been some new theories about why we might expect an extra planet in the outer solar system. And this really started with Shepard and Trujillo in 2014, pointed out that the orbits of the most distant objects in the Kuiper Belt that we know of, these, you can call them Kuiper Belt objects or trans-Neptunian objects, KBOs or TNOs, seem to have an asymmetric distribution on the sky. And that's weird and that's unexpected. And one possible explanation is that there might be a planet out there that is kind of shepherding the orbits of those objects into a sort of confined configuration. And Mike Brown and Konstantin Batygin, starting in 2016, did a lot of work on this. It's often called Planet 9 or Planet X. And there's also been quite a bit of debate about whether or not there is statistically interesting evidence for asymmetries in the outer solar system, which would be the reason that one expects a planet out there. And so, I had been following this saga for quite a while, and now's an interesting time to study the outer solar system because in about a year, the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will be starting operations. And that's going to be the most powerful instrument ever built for discoveries to be made in the outer solar system. In fact, if you're looking at the population of trans-Neptunian objects alone, it's going to multiply the current population size by about a factor of 10. I think latest estimates are that LSST will discover about 40,000 trans-Neptunian objects. Right now, there are fewer than 4,000. And so I thought now's a good time. Well, one, just to get a personal understanding of where things stand in the outer solar system, and two, uh, using all of the available data in a very careful manner on the eve of LSST, if you will, to figure out what we can glean about the possibility of a planet X or planet Nine. And so I came into this work with really no view on whether or not the evidence was convincing, at least the evidence I'd seen in the literature, and decided to take a first principles approach to the problem. And a lot of time was spent defining the sample of objects that you look for the asymmetries in. Because let's suppose that there's a planet, several Earth mass planet, at a few hundred times the distance between the Earth and the Sun. Well, what would you expect to happen if you just placed it there? Turns out it would take about 1 billion years for the planet to shepherd the orbits of the outer Kuiper belt into an asymmetric configuration. So this brings us back to which objects should we even consider as potentially carrying information about a planet. And this means that we should only consider objects that are on long-term stable orbits, orbits that do not get ejected from the solar system or change drastically over the course of billions of years, because it takes a planet billions of years, or let's say 1 billion years, in order to have an observable effect on the distribution of Kuiper belt objects. And so this is a subtle point, but it's a really important one, because previously people had been using a perihelion cutoff, and perihelion is just the distance, the closest approach distance of an orbit to the sun. And previous work had said, well, if it's beyond a certain distance, the perihelion is beyond a certain distance, then the orbits are most likely stable, and so we'll just use that. And that's true, but that also leaves out a lot of objects that actually come closer to the sun, but remain stable over billions of years. And so in order to find the full population, and get a really accurate idea of which trans-Neptunian objects are stable over long periods of time, you actually have to simulate each and every one of them and hundreds of clones of them. And each clone has a slightly different orbit because we don't know the orbits of each object perfectly. We don't know all the 6 Keplerian orbital elements to perfect accuracy. So you sample from the observational uncertainties and you simulate for billions of years what happens to these orbits. And then you find that, some end up being very unstable, but others are stable or metastable, somewhere in between, for long time scales. And then it turns out in that sample, you get a lot more objects than if you had just used a simple perihelion cutoff. Second difference in the sample selection was using objects with smaller semi-major axes. Semi-major axis is just the size of the orbit, essentially. And previous work had only focused on the most distant objects in the entire solar system that we knew of. But it turns out that if you look at simulations of a planet X or a planet Nine, it is expected to produce a kind of sharp break in this particular angle, in which objects closer to the sun should be unclustered in that angle, and objects further from the sun should be clustered in that angle. And a transition from unclustered to clustered at a particular value of distance from the sun had never been observed before, but it was worth looking for by including objects that are closer to the sun and stable and not particularly strongly affected by Neptune. So we expanded, you know, the sample that way as well. And those are just a couple of things. There were a whole a whole suite of improvements, but long story short is we ended up expanding the sample of objects that might carry dynamical information about a planet X or planet Nine from 11 to about 51. And this allowed us to run an impressive suite of statistical tests that really interrogated whether or not there's clustering at all. And if there is clustering, in what angle does it cluster? Because there are actually several different angles that describe a orbit's orientation. You have the inclination relative to the ecliptic plane, but then you also have the longitude of perihelion, you have the argument of perihelion, you have longitude of node, and some other variants. And there have been different proposals pointing to different angles or combinations of angles in which clustering was claimed. So, all of that being said, the tricky thing with the statistical tests is you have to make sure that the effect you're searching for cannot come from observational bias. And this was a large component of the debate over the past decade. Is the reason we're seeing clustering just because surveys are looking in particular areas of the sky, and therefore we're only finding objects with orbits oriented in a certain direction? So, that's a very valid and major concern to any claim of clustering in the outer solar system. And so we looked at clustering on a survey by survey basis, isolating just the three biggest surveys in the outer solar system. But we also developed a new test that allowed us to look at all of the objects regardless of what survey they came from. And the idea behind this test goes back to that subtle point that I was making earlier about the fact that we only want to consider objects that are on long-term stable orbits, because it takes about 1 billion years for a planet to have an effect on an object. So if a orbit is temporary and, let's say, has a lifetime of 100 million years or so, then it might not ever get the chance to get shepherded into a clustered configuration. So what we can do is we can search for that break that I was talking about. The idea that in these angular orbital elements, you expect at a certain distance from the sun and beyond, clustering to basically turn on, and interior to that distance for there to be no evidence of clustering. So I essentially set up a test in which we allow that distance, that wall between the clustered and unclustered population, to be a free parameter. And we allowed it to vary. And we asked, is the population interior to the wall consistent with the population exterior to the wall? And if there is clustering on one side and not clustering on the other, then the answer should be no. And we did this for both the stable population and the unstable population. Let's say there's a planet out there, what would we expect? Well, we'd expect at some distance from the sun there to be a really strong signal in the stable population. And a strong signal would be, no, this population that's closer in is not consistent. The distribution in whatever given angle is not consistent with the population beyond that distance. And you'd also expect for that not to be the case for the unstable population. The unstable population should not have any sharp break because, again, those objects did not have the chance to be shepherded by planet X or planet Nine. And that's exactly what we found. It was really striking and perhaps a bit unexpected, but because this test hadn't been done before. But we did find about the 3 sigma level evidence for clustering in this particular angle called longitude of perihelion. And what's also interesting is we didn't find evidence of clustering in the other angles, in the other angular orbital elements, inclination, longitude of node, argument of perihelion. This is consistent with a planet being out there, but not necessarily the same planet that was proposed in the past. And so the next step was then to figure out, okay, if there's evidence for a planet, then what kind of planet would be most consistent with that evidence? So we ended up running I think the largest suite of numerical integrations ever done for Planet X or Planet Nine. Um, it we ended up testing 300 different combinations of mass, semi-major axis, eccentricity, and inclination for a Planet Nine and or a Planet X, whichever you want to call it. The mass is self-explanatory. The semi-major axis sets the size of the orbit. The eccentricity tells you how squashed the orbit is, how elliptical or circular it is. And then the inclination tells you how tilted the orbit is relative to the rest of the solar system. And for each simulation, for each choice of those 4 numbers, we essentially have the giant planets and the extraplanet and a disk of massless test particles, which basically represent the outer Kuiper belt, these trans-Neptunian objects. And we let the simulation go on for a very long time, and we are then able to record the distribution in these angles. I mean, most notably longitude of perihelion, the angle that we found real clustering in. And we record what does that clustering look like as a function of distance from the sun for every possible planet X. And then we can compare that distribution to what we actually see in the solar system. And so, in essence, we are trying out 300 different planets. And for each of them, we are assigning them a score, like a relative score of how close they got to the actual observed distribution in the outer solar system. And it turns out then you can rank them by how close they got to the observed distribution, and you can characterize the probability distribution in various ways. And the punchline is that the most likely planet is one that's about 4 Earth masses, one with a semi-major axis or distance from the sun of about 300 astronomical units, an eccentricity about 0.3, and an inclination of about 7 degrees. And there's been kind of the latest work on this was Brown and Batig in 2021, and they published their probability distribution for these 4 parameters. And it turns out that our model and their model only agree at the level of about 0.06%. So we're getting a different planet. I think that's probably due to the differences in what I was describing and the way we selected our sample and what we found actual evidence for. And it's really exciting because we're also able to translate these best fit parameters to a probability distribution on the sky, as well as a probability distribution for how bright the planet is expected to be. And it turns out that it makes the prospect of LSST detecting another planet in the solar system very appealing and exciting and potentially possible in the early days of the survey within the first 2 years. So Uh, that's sort of where things stand.
So the what has survived is maybe not the model that Patikin and Brown were envisioning, but the idea of a planet being out there does survive and now seems stronger as a result of this. Am I interpreting that
That's
correctly?
right. We in addition to the test that I described, we also ran tests using the same sort of methodology that others had used in the past to characterize the survey bias of the three major surveys, which were used to argue in the past that perhaps there's not evidence. And we kept on finding the same results that at about the three sigma level. Now, three sigma, to be clear, is not a home run. It's not five sigma, which is, what particle physicists need to announce, we found a new particle.
Good enough for astronomy. Three sigma. That's
Yeah,
you're
it's
there.
it's pretty good for astronomy. And but we kept on finding three sigma level significance for the longitude and perihelion clustering, but not in the other orbital elements. And it turns out that the planet that is favored by our model, even though we fit it only to longitude of perihelion as a function of distance, naturally does not produce strong clustering in the other elements. So it explains itself without us having to tell the model, don't produce clustering in an inclination, or strong, extremely strong clustering, or extremely strong clustering in longitude of node. But the model actually spits out a planet that is much more well aligned with the plane of the solar system than the Batikin and Brown planet, and that naturally should not produce as strong clustering in the other orbital elements. So yeah, the evidence is absolutely holding up for the possibility of a planet in the outer solar system. Although it's a different one than what was expected.
Now, what of multiple outer planets that we don't yet know of? Can that complicate that? Because there's other weird features out there, and one of them is the so-called Kuiper Cliff, where material seems to just drop off as though it's being shepherded. And there was several papers on that quite a while ago, but one of them was potentially a Mars-sized object. Would you even see that echo in this data? Because you're looking for something for Earth masses, and that's where it's leading you. But what of smaller, shepherding planets that might have been interfering in the motions of these objects? I mean, does that just mean that's not a good candidate, loss of information, or can you glean anything from that if there's multiple
Yeah,
gravitational sources
so
out
there
there?
could absolutely be multiple undiscovered planets in the solar system. There could be ones that are closer in and lower mass, as you mentioned, or further out and higher mass, or further out and lower mass. There's all sorts of possibilities. And one is this paper that we're discussing basically is predicated on the fact that you need a certain amount of mass on a certain orbit. And it doesn't have to be one planet, although it's most, I guess, parsimonious. It's kind of the Occam's razor explanation here that it would be caused by one planet. And I think that's probably most likely. But it could be caused by a couple of planets if they're close together and fairly similar in mass. But if there is, if there's another, let's say, yeah, if there's another planet out there that's perhaps lower mass and closer in, it would affect the Kuiper belt in different ways, including, well, there are actually a lot of different effects, including the mean plane of the Kuiper belt for one, and some others that are thankfully not too overlapping with this signal. So, yes, there could be other planets in various regions of the solar system that are yet undiscovered, but I think this signal is pretty robust and is most likely explained by a 4 to 5 Earth mass planet at 300 AU or so. Of course, that could change. And it's really exciting, I think, to be working on the solar system in this era because thanks to advances in technology, we have the largest most advanced digital camera ever built, down in Chile, that's going to be surveying the sky and potentially telling us whether we have missed one or two or more planets in the solar system.
Just the expected amount of Kuiper Belt objects that we don't yet know about that Vera Rubin is going to probably discover, is mind
Yeah,
boggling because there could be any number of small objects out there that, Pluto's, it could be full of
e-
Pluto's, and we just haven't seen them yet, caught them yet, and we're going to very soon.
exactly. And each object carries information about what's out there. And that's, you know, we see a distribution of objects, but it's telling us about the unseen, about what is gravitationally affecting those orbits. And I think that's the beauty of the study of dynamics of the outer solar system. You're using the seen to try to find the unseen.
So, weird question. It's me, of course, I ask weird questions. All right, preserving information of interactions in the past in the outer solar system. Well, there's been some weird stuff happening out there, such as Schultz's star passing through
Mhm.
the Oort cloud. Could we look for movement, gravitational movement fossils left over from interactions with past star systems in the solar system's
Yes,
Earth
well, I
history?
mean that's an excellent question, and that's actually one of the things I'm currently working on. So it turns out that while passing stars can't explain, can't produce the same kinds of signals as as you'd expect for a Planet Nine or Planet X,
Orbitally bound instead of something that's
right?
unbound.
Because the orbits would naturally go back to their previous state. But while that's the case, there are some irreversible processes that can happen in various parts of the Kuiper Belt, both close in the cold population and far out and distant resonances that are sensitive to any interactions in the past with stars. And what's interesting is that that also tells us about where the solar system and where the sun was born, because we think that the sun was born in a birth cluster, but we don't know a whole lot about the conditions in that birth cluster, the density, the lifetime, etc. Um, and this is one, I think, extremely compelling way of essentially doing archaeology on the solar birth cluster, studying the Kuiper Belt for clues of stellar flybys, and that's actually something I'm working on right now. So I'll be excited to share the results when I have them.
I think we both hit on the same question on why you would study that based on what you're studying
Yep.
now. And it's like, wait a minute. What it's preserved on other counts. And the birth cluster is absolutely amazing because, there's work being done that show chemically very similar
Mhm.
stars to the sun out there that may originate in that birth cluster. And you really have to wonder about things like panspermia, exchange of objects in the far outer solar system that may not have actually formed around the sun, but another member of the cluster
Sure.
and got captured, things like that. Although I guess it's harder for captures. It's my sense physically is that it's hard to capture something that far out, but maybe. But the other idea is that 4 or 5 Earth masses start sounding a lot like the
Hmm.
missing super Earth that our solar system does not seem to have. Is that where your thinking's going? That maybe one got
Well, yeah,
tossed out
it's
there.
interesting if we look at the population of planets in the galaxy. If we look at the distribution of exoplanets, we find that super Earths slash sub Neptunes are extremely common, yet we're missing one. So now, while on its own, that's not a reason we should say, oh, there should be a super Earth or sub Neptune in our system. It is remarkable that that is right around the mass of that we're getting out of these simulations. So. That could be it.
And there would be no more, and this is just me opining, but there would be no more fascinating of a type of object that you could find, because at 4 or 5 Earth masses, that's a lot of radioactive decay going on still. In other words, we could start to wonder about things like subsurface oceans, and not like an ice shell moon, but maybe something like an ice shell planet, all the way deep out there, that warms itself through radioactive
Hmm.
decay instead of solar heating. And it wouldn't just be, what I'm saying is, it wouldn't just be a normal run of the mill planet. That's not what's out there. Pluto showed us that no, no, this is
Yes.
very different stuff. And that whatever this is, should we find it, should it be there, whatever this is going to be unbelievably interesting,
Yeah,
scientifically
I
speaking.
absolutely agree. It's also interesting because it's in this regime where we're not sure what the structure would be. Like, we're not sure whether it would have a hydrogen helium envelope and look more like a small version of Neptune, or if it would basically look like a larger version of the Earth, like a scaled up version of the Earth. And yeah, it's just a very, very interesting mass range.
It is, and you wonder, okay, so if it's a mini Neptune, well, those are interesting in and of themselves, because we don't really know that much about Uranus and Neptune.
Yep.
We don't know enough anywhere close, and this would be kind of like that, but yeah, maybe not so much, Or if it's if it's an ice ball, if it's terrestrial or something like that, you get weird questions like, okay, 4 or 5 Earth masses, what does that do to mountains
Hmm. Hmm.
and upliftings and things like that? What's that look like?
Hmm.
So it would just be unbelievably satisfying to find it and wonder about it. Problem is studying it, because that'd be a long way out there, I'm sure. Is so. What's that tell you about the orbit? Does it still look like it would be highly
Yeah, we
elliptical
actually
out there?
found that the orbit is probably more elliptical than previously thought, although in general closer in. So we actually got a fairly tight constraint on its aphelion distance, which was interesting. It just turns out that the features in the data uh, place a pretty strong constraint on aphelion, and of course that is for elliptical orbits. Objects spend the greatest proportion of their time near aphelion, and that actually makes the probability distribution on the sky in terms of right ascension and declination more confined and peaked near the location that aphelion is expected to be. So yes, it's an eccentric orbit and overall closer in than previously expected.
Now, do you expect eccentricity no matter what in any planet out that distant? In other words, could that be preserving information about where it originated from? In other words, you get tossed out. You're at the orbit of, I don't know, Jupiter, and then you get tossed out there. Does that naturally result
Yes,
in
it
an elliptical
does.
orbit?
So I'm glad you brought up the origin of the planet, because one of the possibilities that have been thrown out there is that perhaps it's a captured planet from outside of the solar system. And the fact that we found that the inclination of the planet is probably low and potentially even consistent with zero suggests that it's probably not a captured planet, because it would be very unlikely for the capture to line up so perfectly with the other planets in the solar system. But it does suggest that it was formed within the solar system, probably at a closer distance, probably, as you mentioned, scattered outward by one of the giant planets, perhaps Jupiter. And once that happens, you end up with a highly, highly elliptical orbit that is still bringing it pretty close to the giant planets. And so you need some kind of mechanism that will raise the perihelion of the planet, so that it doesn't interact anymore with the giant planets. And so that, I think one of the most reasonable scenarios for that is actually the effects of passing stars. potentially in the solar birth cluster. Those can take the orbit, which after getting scattered by a giant planet is extremely elliptical, and reduce that eccentricity. And so what that can do is perhaps produce a planet like the one that is predicted with a moderate eccentricity, about zero point 0.3, but not close to one.
You know what would be fascinating, and this is sort of my last question for you, is that, all right, so we have stars passing through periodically and the birth cluster and all that. And we're looking at, orbital fossils, movements that, no, that was created by, some sort of an interaction like that. But you kind of wonder what the surface is, or what geologic evidence might be preserved from, a Kuiper Belt object coming closer to a star than it ever did. In other words, it's been closer to a different star than it ever was to its parent star, the sun. And you might see weird melting and chemistry going on that just doesn't happen in here in the inner solar system. And I know that's far future science, but I'll bet it comes on the table. What do you think? Or
No,
am I
certainly.
crazy?
I mean, I just hope we find the planet soon so we can basically point every telescope, every powerful telescope in the world at it. In particular, I'd be excited for James Webb and Hubble to stare at it for a long period of time to try to glean everything we can about the surface composition of the object, of the planet, and so we can start to imagine and understand what kind of planet it is, what its past was like, etc. So I'm 100% focused on studying the evidence of these these small objects, and I'll continue to do so until this planet is found, or it ends up being clear, like perhaps this was a statistical fluke. But yeah, I would say, I hope we get to study those kinds of things very soon.
It's within the timeline. If the surveys at Vera Rubin begin in 2026, and I know that's been moved forward a little bit, but that's always happens. Anytime we build something, that's what happens. But if you can find it within the early time frame, within 2 years of its beginning its surveys,
Hmm.
Webb will still be there, and Hubble, barring any technical accidents or anything, they'll still be there. So
Yep,
take a
that's
look.
dope.
Yeah, that's the hope. That's the hope. All right, Amir, it's always a pleasure talking to you, and I found this new paper fascinating, and now I'm looking forward to the future papers because of what you're working on now. That's going to be
Thanks,
really
thanks,
interesting.
John. It's always a pleasure talking to you.